I hope you will join very soon. Let us start our chapter we have last day we have discussed yesterday. What is a day before yesterday? Let us recapitulate the matter again, and let us finish the whole stanza itself. Now, the Hooke's law, that is the Hooke's law and principle of superposition itself. What is this? What is Hooke's law? What is simple superposition? What we know here, let us write. Hooke's law and principle of superposition. Now, we know the rectangular stresses, which is rectangular, named rectangular as it is acting along three rectangular coordinate axes, rectangular stresses at a point is related to corresponding rectangular strains at that point. Now, and by how? Through a set of linear equation is a set of linear equation designated as the general Hooke's law, generalized Hooke's law. Now, the Hooke's law is applicable to an elastic body as a whole and related to the complete system. What is going here? Here, Hooke's law is applicable to the elastic body as a whole, to a whole elastic body. And that is let the complete system itself. Let the complete system of forces acting on the body to the deformation of the body as a whole, and relates the complete system of forces acting on the body to the deformation of the body as a whole. Forces acting on a body to the deformation of the body as a whole. Deformation of the body as a whole. Now, the law ascertains that reflection is proportional to force, which produces them. So here also, reflection is proportional to force, which reflection which produce them, produce them within the elastic limit, within the elastic limit. Now, it is a very general assertion without any restriction to the shape or size of the loaded body itself. Now, let us consider a body of certain irregular shape. And we have a point here, 1, and a support here like this, a point here 3, a point support here, a point here 2, and a support here, not given any number. The point 2, this is D1 capital, D2 capital, and it is small d2, and this is a equilateral triangle, and this is the force acting on the point 1 as F1, and this is the force acting on the point 3 as F3. Now, well, due to the action of force F1, the point 2 of the body suffers a deflection, a displacement or deflection, undergoes a displacement or deflection due to F1, due to force F1, point 2 at point 2 of the body suffers a deflection, deformation or deflection. Which according to the Hooke's law is proportional to F1, which is proportional to Hooke's law. Now, this deflection at point 2 take place in a direction which is quite different from that of F1. You see, X1 is more or less vertical, but D2 is not vertical, not nowhere near to vertical, but at an angle acting here. So this may not be of the same. D2 is the actual deflection, so which is totally different from F1. F1 is vertical, but line of action of D2 is totally different from that F1. Now, if it is the actual deflection D2, then we have D2 is equal to K21 into F1. If D2 is the actual deflection, then we have D2 is equal to K2, D2 is equal to K21 into F1 itself. Where K21 is the same proportionality constant is some K21, 1 is the constant of proportionality, constant of proportionality. When F1 is increased, D2 also increases proportionally, but D2, F1 increases, D2 will increase in proportion. So if F1 increases, and D2 is increases proportionally. D2 increases proportionally, and thus uh, and let D2 be the small D2 be the components in a specified direction, say D2 be the component of D2 in a specified direction. Say theta. Because the angle between them is theta itself. Just 1 second. Just 1 second. Now, now D2 will be what is here. Thus, D2 is equal to capital D2 cos theta and more or less equal to K2 cos theta, K21 cos theta F1. Now, if we keep constant, that is, we fix our attention on the deflection in a specified direction itself, then D2 will be, if we keeps our attention in a specified direction, say this direction, then D2 will be equal to a constant multiplied by A21 F1, where A21 is the constant itself. One can consider the displacement of point of the displacement point, displacement of point 2 in any specified direction and apply Hooke's law itself. So what we are doing here, we are having the components, we are having the deflection D2 in an unknown direction, and we are having a direction D2 which is a component of D2 in a known direction itself. And we are thinking that we are getting the direction between this D2 and our external force F1 by means of a constant of proportionality A21. And this applies the Hooke's law in any specified direction of the body itself, by any specified direction over the body itself, of at point 2 itself. If D2 is the vertical law, say if D2 is vertical, if D2 is say vertical, then D2 can be is equal to A22 F1 itself. A22 is not equal to A21 because initially we did not establish a certain line of action of D2 itself. Now we are saying that it is vertical, and we are also saying that F1 is vertical, but they may not be in the same line. But here the constant of proportionality will change to a certain extent, and this will become D2 A22 is equal to F1 itself. When A22 is constant, called the influence coefficient, this A22 is called A22 is the influence coefficient. Influence coefficient. Acha. And for the vertical deflection at the point 2 due to the force applied in specific direction F1 at a point 1. Now, F1 is unit force if F1 is an force, this F1 is an unit force, and then F- then A21 is the actual value of the total vertical deflection and at 2 itself. Then A21 is the actual value of the vertical deflection at the point 2 itself. Now, if a force opposite to F1 is equal and applied at the point 1, deflection will be equal and opposite to the earlier deflection takes place. If several forces all having the same direction of F1 are applied simultaneously at the point 1, the resultant vertical deflection will they produce at 2 will be the resultant of all the deflection which they have produced is applied separately. Thus, the principle of superposition, this is the principles of superposition of small deflection itself. If a number of force acts simultaneously at point 1 itself, and their deflection at point 2 in vertical direction at point 2 is the summation of all their individual deflection, is the summation of all that individual deflection. This is called principle of superposition by Hooke's law. Now, this is considered a force. Let us draw that diagram once again here. This is 1, this is 3, this is 2. So 1 is acting here. And one is F1, this is F3, and this is T2. T2, small d2, theta. Now, consider the force F3. Here we are having another force F3 acting at the position 3, and d2 dash Just 1 second. Okay, now what he is doing, let us consider the force F3. Force F3 acting at point 3. And now this d2 dash, d2 dash is the vertical component force. Let d2 dash is the vertical form of the force, vertical component of the force itself. Now at the point 2, due to a force applied to the specific direction, due to a force applied in specific direction, that is at F3. The question that we examine is whether the principal superposition holds true to two or more forces such as F1 and F2, which acts in different direction at a different point itself. Let F1 applied first, then F2, F3 applied second. Let F1 applied first, and F3 applied second. What happens? Question is, then according to Hooke's law stated before, d2 dash will be, then d2 dash itself is equal to 823 F3, where 823 is then the influence coefficient for the vertical reflection at the point 2 itself. Reflection at the point 2 itself. Now, due to a force developed in specified direction, that is F3 at the point 3. The question that we will examine is whether the principal superposition holds true in two or more forces, such as F1 and F2, which act not in the same direction, but in different direction at different point. Let F1 be applied first, then F3 is applied second. The vertical direction of 2 will be vertical direction, well, deflection at 2 will be d2 A21 F1 plus A23 F3. Here A23 is not equal to F3. A23 here A23 is not equal to A23 dash, because this difference is there, which exists is due to the presence of F1. This is due to the presence of F1 here. That deflection is not exactly addition of the original deflection itself. Then if we apply F1, then apply F1 at point 1. F1 at point 1. Then d2 dash will be, d2 dash deflection is changing always. d2 dash will be A21 F1 plus A23 F2, F3 minus A21 dash F1 itself. So A21 may be different from F1. A21 may not be equal to A21 dash itself. So when F1 is applied, only F3 is acting down. If we apply minus F3, then deflection will become, if we apply minus F3, then deflection will become deflection is D2 dash itself equal to A21 F1, it remains same because originally applied, plus A23 dash F1 minus A23 F2 3 minus A21 F1, A21 dash F1. So minus F3 has a different setup here, which is a bit different here. Next, what we are doing, now the A2 dash itself. Now let us say finally become D2 dash. Then this is like this. Finally become this D2 dash equal to A21 F1, A23 F1, A23 F1, and A21 F1 itself. Since elastic bodies are subject to any other force, this final deflection must be equal to 0. This final deflection must be equal to 0. Thus, must be equal to 0 itself. Thus, what happens? A21 F1, equation A21 F1 minus plus A23 F3, A23 F3, F33 F3 itself, minus A21 F1, minus A21 F1, and minus A23 F3 itself. A21, A23, ठीक है, 1 F3, F23 F3, F21, F1 minus the two column, and F23 F1 itself, F23 F3 itself. So actually, so this will become A21 minus A21 dash into F3 F1 equal to A23 dash F3. This is A23. A23 dash F3 minus A23 equal to F3 itself. And F1 dash is equal to F1 dash. This is there F1 dash, A21 F1, F1 dash, A21 F1 dash, A3 F1 dash, A23 F3 is equal to or A21 minus A21 dash divided by F1 itself F3 itself equal to A23 3 dash minus A23 divided by F1 itself. The difference A1, A2, that if it exists must be equal to that, must be due to the direction of F3. Then the left hand side is a function. We see A21 minus A21 if exists, then it is due to the presence of the action of that is it is due to action of F3 present in the A itself. And then the left hand side of the equation is alone. Similarly, A23 P dash minus A23 is because of the action of F1, and therefore right hand side must be a function of F1 alone. Left hand side is a function of F3 and right. So thus, left hand side should be a function of F3 and right hand side should be a function of F1 itself. So you can safely say we can put a equation, this new equation equal to a constant K. So F is a constant independent of F1 and F3. Thus, which is a K is a constant of independent of F1 and F3. So A2, A23 or A23 equal cell is minus A23 is equal to K into F1 itself. But substituting this equation 3, just we are producing, if we substitute this value, A23 to A21, in our earlier equation, at D2 is equal to A21 F1 plus D2 to F, and A23 dash into F3, the equation will reduce to put in equation 3, then it will become D2 is equal to A1 P1, A1 F1, A21 F1, in fact, A21 F1 and plus A23 F2, A23 F3 minus A F1 F2 itself. This last term of the right hand side is the above equation is non-linear. You see, this is both these two F1 and F2 is multiplying each other. So it is contrary to the Hooke's law. Unless so, K will be equal to 0. Then D2 will become again goes back to the original modified equation F1 plus A23 A23 A21 itself. Thus, the principle of superposition is therefore valid for two different forces acting in two different points. This can be extended by indication to include a third or any number of forces. This means reflection at the point 2 due to any number of forces F2 at 2 is D2 is equal to A21 F1 plus A22 F2 plus A23 F3 plus equal to so and so. Next, let us go a whole body in equilibrium. A force, let us consider a force and displacement or work absorbing component of the displacement. Called force and displacement, or work absorbing component of displacement. Now let us have an elastic body here first, shaped like this. which is have the reaction force here and have the reaction force at A. This is at A, this is at C, and this is at 1 itself, where the force is acting as F1 and it may be displaced due to the effect of other reactions due to D1. There is a force at the point 2, which is F1, F2, and there is a support at the point 3, that is at the point B. So what we have in this force, the external force is acting at the point 1 and 2, as is F1 and F2 itself, and F1 is tensile and F2 is compressive itself. F2 is compressive and F1 is tensile, and we have reaction at the point A, B, and C itself. Now, this body is supposed to be in equilibrium under the action of all F1, F2, F3, and the force of reaction at the point of support will be considered as applied force. Here, we have this force of reaction here. We are thinking of applied output here. So, the displacement D1 in a specified direction, say here, in a displacement D1 is a small specified direction at the point 1 itself. Is given in equation 7. Then a component of this displacement in the direction of the force F1 is called corresponding displacement at the point 1. This corresponding displacement is denoted by delta 1 itself. Delta 1 corresponding displacement at the point 1. Now, it is called, then the component of this displacement in the direction of F1 is called corresponding displacement at the point 1. This corresponding displacement is indicated by delta 1. Well, at every loaded joint, a corresponding displacement can be introduced. So every loaded joint, a corresponding displacement can be identified. A corresponding displacement can be identified. Now, if the points of supports A, B, C does not yield, means they are not deforming in any sense, then at this point, the corresponding displacement obtained from equation 7 will be at the point of, say, delta 1 is equal to A double 1 F1 as per our theory of superposition plus A22 A12 F2 plus A13 F3, and delta 2 is A21 F1 plus A22 F2 plus A23 F3 plus where A21 A1, where A211, A212, and 3 are the influence coefficients, where A2, A11, A21, A23, A13 are influence coefficients. Of the kind discussed later. The corresponding displacement is also called the work absorbing components of the displacement. These displacements are work absorbing component of displacement. Well, with this, we are finishing our syllabus in stress and strain relationship itself. And that's why I'm finishing this class today. Almost nobody has attended. I will go for the next class tomorrow morning from the next module.